So far we've been talking about the motion of fluids, multiple fluids in the subsurface. Talked about wetting and non-wetting fluids as types of fluids in their affinity for the medium which they flow through. When we started out, we posed kind of a question of why these systems, why they should look like this, why there should be this chimney with a smear on it, why ultimately the non-aqueous fluid would stop, as it does here, why it might puddle at different levels. And we've probably answered at least some of those questions to know that the reason it stops is because of a capillary barrier. The capillary barrier really has nothing to do with permeability, but permeability is related to the size of the capillaries, and it's really the size of the capillaries that control what's going on. And we can understand a bit about that by looking at the behavior of individual capillaries, either for porous media as tubes, as you'd think in this kind of bead pack situation here, where you have large grains, large pore throats, small pore throats, and that's the reason for this kind of structure. Of course, that doesn't really explain why you might have a differential saturation if you take what we've referred to as an REV, representative elemental volume, where you have saturations of the two fluids and they depend on which portions of the porous media they're saturating. And so instead of these simple models which give you kind of the breakthrough pressure, or the bubbling pressure as we've called it, for circular capillaries or for parallel plates, we can do a little experiment that forces a non-aqueous fluid into a wetting fluid already saturating it, and we get a curve that looks like this. And we described all the individual features of it, that once you force it in, this is the pressure, the bubbling pressure, so-called bubbling pressure, or PC0, at which you get entry of this red fluid into the system. If you keep on raising the pressure to push it in, it saturates progressively more and more of the pore space, progressively smaller and smaller pores, until it reaches a limit where you can't get any more water out. And then if you back off the pressure, you come down a second curve. We call the first one a drainage curve because it's draining water out of the system. We call the second curve an imbibition curve because it spontaneously imbibes, because the water loves the quartz. And there are limits on this. This is the irreducible saturation of water, SW0 as we've called it. This is the irreducible saturation of non-wetting fluid. And I guess we also talked about the fact that the wetting is hysteretic, so that if you stop it here, stop increasing the pressure here, and then decrease it, it will go across this in some format. And I guess the coup de grace for that was that now, as a function of that, you could, I don't know if I can do this, well, of course I can do this. You could draw these capillary pressures. Actually, why don't I go back to the things that we had before. We had these capillary pressure versus saturation curves, and we used them by standing them right way up or upside down on this system. And so this says that above the water table, where the pressure is 0, if you go up a certain amount, then the pressure in the fluid is tensile. Because the contiguous air pressure, the non-wetting fluid in this particular case, is this green line, which is essentially uniform 0 pressure, atmospheric pressure. So this difference in the two pressures is what defines the capillary pressure. And so as you rise further up in here, just because of the column height, it becomes progressively larger and larger capillary pressure. And so this saturates progressively more and more with air and less with water. And if we flip the curve the other way around, then we get the water pressure changing like a swimming pool, the non-aqueous fluid changing like a swimming pool full of denser than water liquid, And then the difference in those pressures is, again, capillary pressure. And that prescribes the saturations. So what we'd expect to see in this would be that the saturation of water versus the non-wetting fluid changes with depth. And this kind of explains the fact that we have a higher saturation at deeper depths because the capillary pressures are increasing deeper down. So that's what we have used to kind of explain this architecture. And so all of this should now kind of make sense. But now then the question arises, I suppose, if we think about the red fluid getting into place and staying there, then all of a sudden that's no problem for us, right? If it's attached by interfacial tension, it's not going anywhere, and therefore it doesn't pose a risk. But what is important is to realize that it can dissolve, and that's what this stipple is kind of showing off to the right-hand side. If you have water flowing from left to right, then it will dissolve portions of this by flowing above and below this puddle. It has probably a low permeability below it because it must have a capillary barrier below it for it to rest on and for it to overflow the edge and to kind of cascade down. But this will carry the dissolved components. And so the question you could ask yourself is, what is the rate of flow that you'd get across this chimney? Because the rate of flow that you get, I suppose, would be the volumetric flow rate, as we'll talk today, is going to be a cross-sectional area of flow times a hydraulic conductivity times a gradient of head. And so if we know what the volumetric flow rate is, if we multiply the volumetric flow rate by concentration, grams per cubic liter, for instance, then that gives us a mass rate that's removed from here, a mass of TCE or whatever the solvent might be, and that would allow us to calculate, one, how quickly it's removed from here. And I guess we'd find that it's actually removed quite slowly because these concentrations are parts per million or parts per billion. And it also tell us what the concentrations might end up as we go downstream, which might be two pieces of information we want to know. And I was going to show you this. I am going to show you this. Where's my email? Look at this. Someone was looking. You didn't want to be here on the first Tuesday of classes, but apparently someone else did want to be here and wants to know all about your lives and what you were being subjected to at the time. Anyway, I thought that was interesting. I looked through my grade book and I couldn't figure out from the name, Cesar Lattes, there wasn't anything. Well, I don't think it's a hoax. I think no one would write such a thing, would they? Should reply. Where's it gone? Is it there somewhere? Yeah, it was the stuff we did. Can I reply? Does it reply? Where's it? Why won't it allow me to reply? 61 views already for our class on the first day of classes. Well, I can't see where to reply, so I'm not going to worry about it. But anyway, you're lucky to be here. You really are. Even though you don't believe it yourselves. Anyway, so what we'll talk about today is trying to figure out exactly how we evaluate such rates in this system. And so I could use the notes here, but I won't. I could use this material, but I'm going to do it just on two individual sheets of paper that I have from a previous year rather than scribble them out. So this is what we'd like to be able to talk about today. So you've seen some of this before. So it's been used on previous occasions. So these are the 2 pages just to zip through it. So if you want to write it down or not write it down, it's your prerogative, but it's not going to be very much that we'll deal with. So the idea is that you've seen Darcy's law in 452. You know that it relates to maybe flow within a core, and you know that it defines a Darcy velocity here as the product of a hydraulic conductivity and a head gradient over length. The length of this core that's filled with porous media is this. I guess you could define that as two components, which are Z and P over gamma water. I guess this could be 1 and 1. And if this is coming out at atmospheric pressure, which I guess this would suggest, the pressure here is 0, then this would be Z2. And we know that we define head as equal to the elevation plus the pressure head plus the velocity head. And the changes in velocity, and typically the absolute velocities, are small enough that we typically get away from that. Remember that this term represents inertia, what energy, what force it takes to accelerate a fluid. They're not accelerating very much because they're going at very slow velocities. And most of the energy is used up not in accelerating the fluid, but by viscous drag. This is the friction factor, essentially. Hydraulic conductivity is essentially a friction factor. So we can define Darcy's law in terms of the change in head or pressure, which is really the head over the length. It's negative because it flows in the opposite direction from the positive pressure gradient, head gradient. And if we multiply this by a cross-sectional area, which is the end of this tube, we get a volumetric flow rate. And so if we, as we said, if we wanted to calculate the mass rate of loading, it's equal to a volumetric flow rate multiplied by a concentration. And the uppermost concentration would be the maximum solubility of that component in water. So immediately, if we know what Q is, we'd be able to calculate what the mass removal rate is and what the mass loading downstream is. We define the head gradient in terms of a rate of change of head over length. So if we draw this core horizontally, it would exactly look like this. So far that we're only talking about one fluid, so we've only got water saturating the pores. And so if we define it in terms of these terms, we can substitute for Darcy's law written in terms of hydraulic conductivity and head, we can substitute this magnitude of head. And so it's important to realize, one, that we've thrown this term away, we don't care, but head includes both pressure and elevation. So this term here, bless you, we could substitute by taking this term here and merely adding it in here, in which case we'd end up, if you take the differential outside, we have pressure over unit weight multiplied by Z. And since this is operated on by differential, we could differentiate each of these terms. So this would be, and I can take this out and then add it later. So this differential is equal to dP dx, just this. I guess it does need that other term. 1 over unit weight, and dz dx. So if you think about the core being horizontally or vertically, those are two kind of orientations you could imagine that it would take. If it's horizontal, then if we draw our coordinate system so that x is horizontal and z is vertical, then this Darcy velocity is the product of a pressure gradient between upstream and downstream, but multiplied by the change in elevation, dz, as a function of x. And so since x is horizontal and z is vertical, they're orthogonal to each other. So for this case, this has to be equal to 0. There's no component of z in the x direction because it's vertical. And so it would be correct for us to write this equation in the x direction as equal to minus k dh, actually dp dx. But if we write it in the vertical direction, which is what this is saying here, is that this again is the negative hydraulic conductivity multiplied by dp dz in this particular case. So in other words, we just put as ddz in front of it. So now this term is equal to 1. And so all of a sudden this term doesn't disappear as it was in this case. So in this case we have to include it. So it's important to realize why we can write it in terms of either head or pressure and how it looks differently if we do. And physically what this means is that this term here is equal to 1. And so if you draw a diagram of pressure change as a function of elevation, if you're in a swimming pool and your pressure changes with unit weight, then by definition you'd think that if the pressure was changing linearly with depth, then there's no motion in the fluid, static fluid. This is exactly what this term represents. So when you write it in terms of pressures, you have to include the factor to allow for the unit weight of the fluid. If the pressure distribution in this fluid was shallower than that, then by definition this would mean that the velocity of the flow, if your swimming pool, so you take this in a swimming pool, you go down with depth and you find out that the pressure changes with unit weight linearly. So that from this equation here, which you've seen before, you would calculate that pressure is equal to P0 plus the depth times unit weight. That's all this curve here is, this thing here. If you have a pressure which is steeper than that, then this pressure within your swimming pool, if it was filled with porous medium, fill the swimming pool with porous medium and then fill it up with liquid. If the pressure distribution in that fluid were flatter than that, that means that at any particular depth that you find yourself, say this depth here, the pressure here is higher, this pressure here is higher than it would be for the hydrostat, that means it's flowing upwards. If it's less than that, that means the pressure, the flow is downwards. So if you write the equations in terms of pressure, then they would look like this. If alternatively you write them in terms of head, and this would be negative on this side and positive here. And if you plotted them, then those same curves, then this would be flowing upwards. Not sure what color that is. I guess it's blue, is it? This would be flowing downwards, and this would be stagnant. So the three curves here, the one, if you plot pressure difference with elevation, then that is equal to just the pressure you'd see in a swimming pool. Any pressure that's larger at a given depth than that means it's flowing upwards, less than that is flowing downwards. And the reason for this would be that if this is the swimming pool, if I draw it off to the side here, then if you take any point here, then this would be equal to P over gamma. This would be equal to elevation. And so I don't know if I can draw a squiggly bracket, but I'm trying to. This magnitude here would be the head. So no matter if you choose this point here or this point here, where these arrows would just relocate themselves. This point here, the pressure would be equal to the depth of this below the surface, and the elevation would be the depth above the datum. Every single point along this, if the fluid is static, has a uniform head, and therefore is not flowing. And so it's kind of a complicated thing to think about if you do it with it in pressures, that you have this extra term here if you're moving in the vertical direction. But perhaps it's relatively straightforward to understand it in terms of what it means in terms of heads. So you just need to remember that. And so the two ways that we can write these expressions are that if we write it in terms of a Darcy velocity, it's equal to the hydraulic conductivity times a gradient of head with length. If we substitute that the head is equal to a pressure divided by a unit weight, in other words, this is a component of the head, then we can exchange it into this. Unit weight is equal to density times gravity. Pressure is this. And we can also rearrange this so that this term here is also the equivalent of a permeability. So you've used this conversion already, that this term here. The units of uppercase K are hydraulic conductivity and its velocity, meters per second. Density is kilograms per cubic meter. Gravity is meters per second squared. Pressure is a stress, and X is the length. This permeability is strange units that don't, at some level, make any sense. They're units of length squared, meters squared, and viscosity is Pascal seconds. And one way to think about this is that you can think of permeability as proportional to the pore diameter squared. And so one model for permeability that you can get from thinking about a bunch of capillaries all held in a bundle would be that the permeability is equal to the diameter of the grains is typically taken at, although it should be the pore size, times the porosity divided by 36. Won't derive where that came from, but porosity has no units, 36 has no units, and pore diameter has length squared. So it'd be the same as this term here. So that's kind of a refresher of what you'd have understood presumably from 452. So you can write Darcy's law either in terms of head and hydraulic conductivity or permeability and pressure. Petroleum engineers and geothermal engineers tend to write it in terms of pressure because pressures are high and therefore the viscosity, and temperatures are sometimes high, and therefore the viscosity of the fluid that's flowing makes a difference. And if you use permeability, it completely removes any characteristics of the fluid out of the evaluation. Here, the hydraulic conductivity has to be measured at a particular temperature and a particular fluid. Permeability is independent of the type of fluid, gas, liquid, nitrogen, air, methane, oil, water, doesn't matter what the fluid is, because independently you evaluate the viscosity of that fluid here. If you use hydraulic conductivity, this is specifically for a particular rock, but also for a particular fluid that's flowing at a particular temperature, because that affects the viscosity, which is all embedded in there. Okay. So, enough said. So Darcy's law, you've seen it before for a single fluid. So our intent today is to talk about how we could represent that for multiple fluids. And this is probably the easiest way to try and explain that. And so you take the same core we had before. You have an upstream fluid pressure which is applied on that core, which we'll call dP. And you can think of doing this. And actually I'll go back to this. This is the thought experiment. So the thought experiment is to do this. And so you could imagine that the real porous medium you have looks like this. The wetting fluid water is the red. The green is the non-wetting fluid. And we know that the non-wetting fluid will tend to go into the most open pores first from our capillary pressure versus saturation curves. So you'd think that this highway through here would be occupying all the largest pores in the system. And so what we might think about doing is if we centrifuge down this porous medium so that we segregated the largest pores and the smallest pores. We'd have to do that, I suppose, but we can just think of it as being occupied by two different fluids and the pore sizes being uniform throughout here. Then we'd have these two different areas. And we could imagine that those different volumes of the porous medium that are filled would change depending on how much of this new fluid we put into here. So if we have an island of this non-wetting fluid here and we flow fluid from one side to the other, clearly we're only going to get red fluid out of this on the right-hand side because the upstream and downstream aren't connected with the green fluid. If we put in green fluid, the non-wetting fluid, so that this island grows, then it will grow so that it spans the control volume. And at this stage, we'd expect to, if we had a pressure gradient between upstream and downstream, to be able to get both fluids out of it. We get the green fluid and red fluid simultaneously. If we keep on adding more green fluid than the red over time, then the green fluid would change the saturation. And at some stage, then the red fluid would not be able to flow from one side to the other. So that's the kind of process that we like to be able to follow. And so to do that, we'll try and divide the system into one where we centrifuge it down and we look at the behavior of those two fluids in isolation. So this is the thought experiment. We have a portion of the core which is filled with a wetting fluid. So I'll just remind myself because I'll forget. It doesn't matter, but it's just congruent with that other figure that we had. And so the idea is that we have these two areas. So to push the fluid through here, we can imagine having for the red fluid a pressure gradient between upstream and downstream. So this black is the pressure that's applied on the red fluid, and the pressure gradient that it applies is dpdx along the length of the fluid. We know that if we have a wetting fluid and a non-wetting fluid, then from our capillary pressure diagrams, the pressures aren't necessarily the same, so they can be offset by some amount. So this green height here relative to upstream and downstream would be the capillary pressure differential between the two pressures. So this would be the pressure in the green fluid. And so what we can do is we'd like to, when we're flowing fluid through the system, describe it in terms of the total area of the end of the core. And but we don't have that. We can define the area that's the red fluid as being the total area times the saturation. So if all the pore spaces in here are the same size as each other, then we'd expect the area of the red fluid to be the total area of the end of the core multiplied by its saturation. So if the saturation of the red fluid was 0, then the area would be 0, and the area of the green one would be 100%, and it would fill the whole area. If it's 50-50, as it's shown here, it would be like this. And if it was 100% the other way, it would be, this is 100% and this is 0%. So what we could do is we could now write Darcy's law in terms of this. And I don't want to do this. In terms of, no, actually I do want to keep that. Okay. So we write Darcy's law in terms of this. This is the volumetric flow rate of the red fluid that comes out. It's equal to the cross-sectional area of the fluid multiplied by the permeability, the viscosity of the red fluid, and the pressure gradient. That's just Darcy's law written for this little semicircle or half circle. And if we substitute the value for this area in here in terms of the total area times the saturation, then we get this expression here. And so the convention is that since we know that this saturation, we can define it, then we can refer to this as something that we'll refer to as relative permeability. And so all this is a multiplier by which we multiply Darcy's law to be able to count for the relative proportion of the core that's filled with the red fluid. In other words, the saturation of the red fluid. And we would know the saturation, and we'd know the total area of this core, but we don't know the red area, cross-section area. But the product of these two gives us the red area. And so what we can do then is we have an expression that says the total area of the core times this relative permeability to fluid 1 times the permeability of the core, which doesn't care what fluid is saturating it. It's a function only of the porous medium, the viscosity of the red fluid, and the pressure gradient that drives it. So that's the amount of the red fluid that's coming out as we apply this pressure to it. If we do exactly the same analysis for the green fluid, where we know the relative area of that, we do the same thing. We end up with the volume of the green fluid that comes out. Again, the total area of the core in each case. This is the total area. And now the relative permeability, or the saturation, multiplied by the permeability of the core. Doesn't care if it's a green or red fluid. The viscosity of the green fluid, viscosity 2, and the pressure gradient along the length of it. It would be the pressure gradient in the fluid 2 from upstream to downstream. Actually, it might be very similar to the pressure gradient of fluid 1. And the reason for that is that the saturation isn't necessarily changing, it's just happily flowing along in these two different pipes essentially. And so we can do that. So we have two different expressions. So now all we need to think of is how to be able to define this relative permeability. And so the easiest way to think about that is if we draw a diagram, which I'm going to draw here. And that is that we think of the red fluid. So if the red fluid completely fills the tube, then it's a saturation of 100% water. And so 100% water, if we plotted water saturation versus water saturation, seems like a stupid idea, but if we plot that, then 100% saturation, we'd be at 100% saturation at this point here. If we're at 0 water saturation, so there's no red here, then we'd be at this point here. And between these 2 points, we'd have a curve that looks like this. If we did the same for this curve here, we have a relative permeability, but it's really a saturation of the green fluid. Did I say red fluid? So if we plotted that on the same figure, at 100% green fluid saturation would be here, at this point here. And on this vertical axis, if this was the saturation, it would be here. At 0% of the green fluid would be down here. And at all points between that, if we just increment it, so it's slowly going from no green to all green, we'd be traveling along this curve here. No green to all green. So this is saturation of water versus the saturation of water. But we've replaced the saturation of water what we call a relative permeability. So we could also call this term here, which varies between 1 and 0, a relative permeability. And we know it immediately from the saturation. And so the reason for thinking of it that way is that we could think about the curves that we've already looked at. This curve looks familiar. This is capillary pressure versus the saturation of water, the same horizontal axis that we have here. But we know the reasons that we have these curves that look like this is that one, this curve asymptotes to this irreducible saturation here. and it also asymptotes to this irreducible saturation here. So these upper boundaries on this we think might be no-go areas. So conceivably, as is drawn here, we might think that these curves should actually, instead of looking like I drew them, might look like this. So this is 100% NAPL saturated, so it doesn't change it. At this point, it comes down here to this point here. And if we do the same for the red curve, then we get these two behaviors. One going across here, one coming down here, one going across here. And so this is kind of the curve that we've done. We've just done a minor adjustment for the fact that when the saturations are below these irreducible saturations, this is the amount of water that we can't get out. We might think that these curves would represent the true relative permeability of the system. So, and it's quite a useful approximation to do. And that's all that's drawn here. So physically, what that means is if we do an experiment, and actually I can do that here. We can imagine doing an experiment where we take a porous sample and we force multiple fluids across the length of it from an upstream pressure and a downstream pressure. We collect the two fluids, separate them so we know how much of each one is flowing, and so we could go back to that expression for the volumetric flow rates and we could calculate exactly what these relative permeabilities would be for that porous sample if we were to do that experiment. And we'd find that the results would look not quite like this X curve that we just drew, but would look a bit more like this. And that is that there's this no man's land on either side that we can't get access to, and that when we push fluids into it, we measure a relative permeability which is in drainage mode, that climbs up as we increase the saturation of the non-wetting fluid. And then when we decrease the saturation of the non-wetting fluid, it comes down again, but not on the same pathway. And so if we look at what these curves would actually look like, and we do have some examples of that, I guess below this, would be something like this. So our end goal in all of this is to determine what these relative permeability curves would be. And so hopefully we've done it reasonably rationally. Not sure whether I've changed my colors around. This is what we did previously. Actually, what we did first was this. By just saying that the saturations should scale with the relative permeabilities. And all this represents is the proportion of the end of the core, which is either red or green, is proportional to the saturation. That's exactly what this is. We said that that doesn't make much sense because if we do that, then we're ignoring the fact that we're excluding access to these irreducible saturations here. And so the curves might look like these two curves here. And that could be a reasonable a rationalization for us because we have these irreducible parts where we end up with a different permeability because we are not changing the saturations in these portions. And actually, if we do the experiments to look at the relative saturations, we get curves that look like this. And so this is the non-wetting curve here. And so in this particular case, they would conform to these geometries. So when you have the non-wetting fluid that may be, I don't know, if we look at the non-wetting fluid and the wetting fluid, maybe this is 80% saturation And maybe this is 20% saturation. Maybe this is 2080. And maybe this is 60-40. My hand's seizing up. And 40-60. And it kind of explains the process here. So now you have a connection between upstream and downstream for the green fluid. You'd expect that to give you 100% flow for the green fluid, but the red fluid, the relative permeability is 0. And so if you use that to calculate the volumetric flow rate, Q, we called it Q2 before, right, is equal to area times relative permeability 2, permeability fluid 2 times pressure drop of fluid 2. And for fluid 1, it would be Q1 is equal to the area of the core, the relative permeability of fluid 1, the permeability of the core, same for both fluids, viscosity 1, and pressure gradient in fluid 1 along the core. So each one of these would give you the volumetric flow rate, or if you wanted to, you could divide through by the area and get the Darcy velocity. But the important thing is this is the area of the core, and it's the same in both of these, the cross-sectional area of the full core. What allows you to scale the proportion of the core that's filled with one fluid is this relative permeability. So if we're here at 80-20, then this saturation, the non-wetting fluid saturation is 80%. I guess it would be here. So this would be 20% water. This would be 80% non-wetting, right? It goes the other way. 0 non-wetting, 100% non-wetting, 0 water, 100% water. And so if we were to calculate what the relative permeabilities would be, the KR1 would be this. So this would be KR2 equals 1. KR1 equals 0. Right? The two values are here. So the permeability to water is 0. The permeability to the oil, the wetting fluid, is 100%. If we go to the next point on the curve, so this would be 60% non-wetting. So that would be this point here. So this would be 60-40. Then now these would be the values that we would use, and they define the transmission characteristics. So I'm going to just put them in brackets here. The bracketed values would be what? The non-wetting fluid would be something like 55% or 0.55. It's usually done as a decimal. Perhaps it's better to keep it as a decimal. And the water is, I don't know, this is 0.1, so maybe 0.05. I'm just eyeballing these. The next one would be 60% water and 40% non-wetting. So this is 40-60. So the non-wetting one now would be only, I don't know, I would say less than 0.1 if you look at this scale. This is 0.1. And the transmission of the water would be, I don't know, 0.25. And And then finally, when we get into no person's land, no man's land, then I don't know if this is, it's kind of undefined. This would be 20% NAPL and 80% water. Then this is 0.4. And this is 0. And so in all of these cases, if we substitute these relative permeability magnitudes ahead of the expression, same area of the core face, same permeability for both core materials because it's the same soil, rock. Pressure gradients are probably the same as we saw earlier in our little figure. Whoops. If you remember in this, very specifically, the pressure gradient, these are parallel to each other. So there's actually not very much different between the upstream and downstream. So we can take those as being roughly the same. There's a difference in pressure. That's the capillary pressure, which you know from our capillary pressure versus saturation curves. And so the behavior we have is this. And I guess we notice a couple of things. If I just drew a little cameo of what we drew before for our relative permeability versus saturation curves, our so-called X curves. So this is saturation of water, 1 and 0. Remember we had a curve that looked like this. And this is relative permeability of fluid 2 and fluid 1 for these two. So if you take any proportion that goes through here, then you'd immediately see that the relative permeability to the non-wetting fluid plus the relative permeability to the wetting fluid add to 1. They have to because they're on this line here. Take any vertical curve through these X curves, they've added to 1. If you add these two relative permeabilities to each other, which is this dotted curve here on top of it, it's nowhere near 1. It doesn't go across the top of this at all. And so that's because there are portions, I guess in this particular case, you can envisage it most, is that the red fluid's not flowing. The green fluid, non-wetting fluid, only fills up a portion of the section. And so if this is not flowing, then part of the flow through the section is blocked. And so that's the reason that these don't necessarily add up to 1. Because it's flowing in the green part, but the red part is stagnant and not flowing. When you get to the opposite saturation, at some stage the green fluid will snap off and it will only flow in the red part. So anyway, I tried to explain that. It's not necessarily a super simple concept, but the outcome is kind of important for what we do. So let's go back to this. So all we did was go through this idea here. We could write separately for flow within the red tube and the green tube Darcy's law. If we take the proportion of the area that's filled by one fluid as a saturation, we can describe that as a relative permeability, and we can measure that relative permeability on a core by doing a flow test where we measure the transmission through the core at different saturations. If we do that, we get curves that look like this for the non-wetting fluid, which is hysteretic, and for the wetting fluid, which is also hysteretic. And one way to look at these curves is to place them directly on top of the capillary pressure versus saturation curves, which is what is kind of shown here. And so the features of it are that these exclusion areas are the irreducible saturation of the non-wetting fluid. And this is the irreducible saturation of water. You can't get any more water out than this particular part here. And that you'd expect these curves to be hysteretic. And they conform exactly to the capillary pressure curves that are applied on top of them. And so if, for instance, we could do it, I suppose. If, for instance, you have a geometry where it looks like this. So this is me drawing, my attempt to draw what a capillary barrier looks like with the stuff sitting on top of it, what the chimney looks like that sits on top of here, and if you want to calculate the volumetric flow through here of water, then you merely write that as volumetric how am I going to write it? Q1 equals V1 A1 equals A dpdx. So from this you want to be able to choose exactly what your components are. So you need to know what the permeability is of this material. I don't know what it is. K equals 10 to the minus 15 meters squared. Wouldn't be an unreasonable magnitude for something. That might mean nothing to you. Cross-sectional area that flows through. This is this area here. And the other thing you need to know is where on this capillary pressure versus saturation curves you find yourself. And so you would know that here your curves could look like, I'm just going to do it simplistically, and I'm going to use the same color scheme we used before, was that this looks like this, and this, and this. This is the saturation of water between 0 and 100%. This is the saturation of the non-wetting fluid between 0 and 100%. And if this is the water that you're looking at, which is the wetting fluid that we looked at, then how would we do that for this? We need to know the characteristics of the saturation at this point. We'd need to know the saturation of water. Let's say the water table is at the top. And so the saturation of water might be 80%. And so we would have a curve up here at 80%. And then the question is, which of these relative permeabilities do you use? So this is the relative permeability. It goes between 0 and 1, as saturations do. And so to round out this calculation, you would know this. You know that the viscosity of water is equal to Anyone remember? Anyone not watching cats fighting? Of that order, you'd know a pressure gradient because you'd know maybe the gradient of the water table across here being dp dx. And so you have both of these. And so all you need to know is what this is for the water. And so the appropriate one for these would be that this would be the relative permeability of the wetting fluid, which we've called fluid 1. And this would be the relative permeability of the non-wetting fluid, which we've called fluid 2. And we think that in this chimney that the saturation of the non-wetting fluid might be so small that it's not connected from one side to the other, and it's also held in force by capillary forces. So this is typically the one that we would want to calculate. And so we could calculate the flux of water is equal to Q1 in this particular case. And if it's carrying a solute with it, then the mass rate that it carries the solute with it would be volumetric flow rate of water multiplied by solubility. In other words, how much of the non-aqueous fluid dissolves in water. And this would be how much it would carry downstream. So you'd calculate its loading. So that's pretty much it for talking about flow of two fluids. So not a particularly easy topic, but the two figures that we'll use in this class stacked on top of each other are the capillary pressure curves, which are defined this hysteretic curve for drainage and then imbibition, and the scanning curves that go across it. The vertical ordinate of this is a pressure differential between the non-wetting and the wetting fluids. Physically, what that differential looks like is this magnitude here, this constant magnitude on top of the pressure gradient. If the saturations aren't changing, so in other words, if the cross-sectional part that's red and green are in the same proportion with time, they don't change with time, then this is just like flowing in two different pipes, a red pipe and a green pipe. There's no change, and so you're not moving anywhere along this curve. You're not changing capillary pressures, so you're set in a static location on this curve. That static location in this curve represents a division of saturations between the wetting and the non-wetting fluids, which is this intersection on this. And if you go up to here, then these are the two relative permeabilities that you'd use. One would be the relative permeability of the wetting fluid, which is the red curve here, which has to go up to 100% here. It's not really very clear how it gets across this no man's land. And the relative permeability of the non-wetting fluid, which would be the lower part. And so if we know how to use those, we know exactly how to be able to calculate flow rates of water in this particular case across the system. Or if we would take a straw on this lens here, which has a little bit of water in it, I guess this would actually be the opposite, right? What would you expect the saturations to be here? If you drew your REV at this particular location, saturation of the wetting fluid, saturation of the non-wetting fluid, what would you expect those to be? Thoughts? Non-wetting, what do you think? In the puddle, would it be high or low? That right, you think? Or wrong? Would I lead you astray? Sean. Oh, even you were looking in the sky. Do you think it's high or low? Do you think 80's right?
I mean, for the non-wetting fluid, if it's a denap, yeah, it should be denap.
Yeah. Good. All right. I think so. So, in the non-wetting fluid, you could do exactly the same. You could now calculate the flow at 80% non-wetting saturation, 20% water saturation, and these would be your individual portions. And so now, if you wanted to calculate the volumetric flow rate in fluid 2, which is the non-wetting, it would equal the area times the relative permeability of the non-wetting times the permeability, which isn't going to change. What did we say? It's this. Viscosity of the fluid would be different, and the pressure gradient would probably be the same. The pressures aren't the same, but they would track across it for the same argument that we had here, that this offset is the same throughout along the core. And so now the question is, what's the relative permeability of the non-wetting? It is, of course, this one. Wetting. So it just depends what the fluid is that you're flowing through. And so, not so terribly involved. The idea is that if the saturation isn't changing, you can think of it as flowing in two separate pipes where the relative cross sections are fixed. And if we know what those relative cross sections are from the saturation, then we can use that as an index, which we call the relative permeability. Relative permeability is just the relative proportions of these two fluids. If we look at what those saturations, how those saturations would change as we saturate core with real fluids, then it starts looking like this. If we look at real values, I guess we have some here, it would look something like this. And the characteristics of this really allow us to directly calculate the rates at which we'd get flow through the system. If it's flow of the water, then that gives us the water flow, but we might expect that to carry some dissolved components with it, in which case we can calculate what that mass loading would be, or mass removal rate. And if it was an apple that was flowing, we could calculate what that would be flowing at as well. And if we look at real fluids, then the sum of these two red and green lines actually don't add up to 1 as they would do if we just did this X curve, which is something for us to know. And what they physically mean is that at this left-hand side, only one fluid flows and the other fluid doesn't. There's a central portion where both fluids are connected between the upstream and downstream, and so both flow if you put a pressure differential between them. And at some stage, at high saturations of water and the non-wetting fluid at low saturations, then there's only one fluid connected across the two parts. And therefore, that's all you have to worry about. So that's it.